Hello, my name is Richard Crawford, and this is my submission video for Project 3 of Summer 26 semester Fluid Mechanics with Dr. Ozbay. We're going to start by opening a new standalone Fluid Flow Fluent project. You see here I've already assembled a 40 hertz and a 60 hertz wind tunnel. Effectively, the process is exactly the same, except you're going to have a different velocity. So per the description and the instructions on the assignment, we're supposed to have the frequency, we're supposed to have the velocity of the test section dependent on frequency. So I use this formula, 0.2489 times the frequency minus 0.3718 to derive these velocities. And so that is the U velocities that will go into our Fluent simulation. All right, so to start, I'm going to go ahead and name hertz wind tunnel. And then we're going to open a new design modeler geometry. All right, so we're going to focus on the XY plane. Let's select the positive Z so that we're staring right at this. We're going to change our units to inches. And I'm going to go ahead and start making a line. And we're going to start at the origin and move over an arbitrary distance. In a minute, that'll become important, but right now we're just creating a line. So dimensions. So our first horizontal line is going to be 15 inches. Second horizontal line is going to be 24 inches. And we're just going to keep going down the row here. All right. So dimensions. Okay, H3. We got 15, 24, 12, and 42. So from here, I'm going to just take a line from each side for 6 inches. which is our test section height. Height of 6 inches. And a height of 6 inches there as well. Now we're just going to continue across, drawing lines. I don't know that this is the most efficient way, but it's worked out well for me so far. Let's delete that one actually. Let's make sure our dimensions are correct first. So H7 is going to be 15. H8 is going to be 24. H9 is going to be 12. And now we just need one more line to connect. And we can verify that that dimension is also correct. H10 is also 42 inches. Okay. So now that we have our blank box set up, I'm going to go ahead and start creating our contraction chamber and our diffuser. So right here we have a 6-inch tall rectangle. We need to end up with 22 inches for the settling chamber. So I need to add an 8-inch line to this point here. All right, so an 8-inch line on the top. Eight-inch line on the bottom. Now this entire front space will be 22 inches tall. All right, now we can go ahead and delete this section, delete this section, and we need to draw 2 more lines for our settling chamber. This may be 15 inches. And another one down here. All right, then we can delete this line and this line. And we only have to connect the dots from here to here. Alrighty. So let's go ahead and select this line. This line can both be deleted. Let's go ahead and draw two new ones. Let's do a horizontal. And another horizontal. And then we're going to do an angle. Okay, so horizontal 17 should be 42 inches. Horizontal 18 is 42 inches. 3 degrees above 180. And 3 degrees below 180. Then we can delete this and draw a line to connect the dots. So now we have concept, surface from sketches, apply, and generate. All right, so now that we have a surface, we can save project, and geometry is done. Let's go ahead and close that one and move on to mesh. All right, so let's try this insert method. Apply the geometry. Change it to triangles. All right, so we're going to go ahead and generate the mesh. Change element size. And hit generate again. We're going to update. And now mesh is checked off, so we can close this down. One thing to make sure you do before you leave mesh is to create name selections. For the inlet, the outlet, and for the wind tunnel walls. So next we'll go into setup. 2D double precision. So there's our surface body. Everything's looking good. Let's go make sure that we change this to viscous laminar model. Okay. Everything else here is good. Materials, fluid, air. Should be standard, but just want to make sure. So just so once we have everything sorted out, you want to go to boundary conditions, and we need to make a velocity inlet matching our frequency, our calculations based on frequency. So for the 20 hertz case, we're going to do 4.6062 meters per second and apply, close. And then the outlet is just going to be a pressure outlet. 0, reverse flow, apply. And the walls are just going to be stationary walls, no slip condition. Apply. Okay. Now that we have that, I also want to go to surfaces. It's going to start at 0 and go until 2.362 meters. I calculated separately. And 0.0762 meters tall. Create. All right, so everything's looking normal. Now we move on to initialization. Once initialized, we can move on to run calculation. Number of iterations, I'm going to do 2000 and calculate. All right, now that calculations are complete, I can go back in, make a couple contours. Let's see, pressure. We're going to start off with dynamic pressure. Select all, display. There's the static pressure contour and the total pressure contour and velocity. And then we'll make XY plots for dynamic pressure along the line that we created. That looks good. So we're going to write to file. And then we can also do the same for static and total pressure. And then total pressure. Okay, so now that solution is checked, we can close this down and move on to results. So we're going to do a pressure contour. Grid and 10. Pressure contour. And then let's also make a velocity contour. Now we can create a couple charts. Using the data that we pulled out of plots earlier. Do 40 and 60. Third column. And fourth column. Now we have a lovely dynamic pressure curve. The lowest being 20 hertz, and as velocity increases, so do the dynamic pressures, which makes sense. So that's dynamic pressures. Let's go ahead and make another chart in the same way. Static pressures. It's 40 hertz and 60 hertz. We're going to change the file. Static pressure, column 2. Column 3. And column 4. Apply. And in the inverse of the other graph, as velocity increases, static pressure will go down. So the highest velocity has the lowest static pressure, which makes sense. So we're going to do one more pressure chart for total pressures. All right, so 20, 40, 60 hertz. Yeah, total pressure graph. Total pressure graph. Third column. And total pressure graph. Fourth column. Let's go ahead and apply. Okay, and as we suspected, the total pressures are going to be roughly equivalent, constant as you go through, as you go down the X values. Now, there's one last chart we're going to make for velocities. Title it velocities. Hertz. And just like the others, go down the line. Velocity graph. Velocity graph column 3. And velocity graph column 4. And in the same way that the dynamic pressures increase with velocity, so will your velocity graph. So I'm going to go to title page. 20, 40, and 60 hertz. Internal simulation. Richard Crawford, apply, refresh the preview. All right, now should have all of our captured data, dynamic, static, total pressures, and velocities. Nice, easy to read graphs. I think that looks good. So we can go ahead and publish as an HTML. And we're done here. Lastly, let's just make sure that our reports look the way we want them to. All right. Looks good to me. Well, I appreciate you guys sticking with me. Have a good day.